Okay, so I think we're more or less ready to go. Well, thank you, Lavinia, for offering to give us a talk and sharing your insights. And we've got one more person, so now we've got 6 people in the room. Okay, and we're very pleased to have you to give a talk. And so I guess the talk is going to be Gravitational Drama, the actors on the backstage. So take it away.
Thank you. Thank you very much for having me here. So yeah, I would talk about the gravitational drama and which the actors are. So why is gravity important? Well, for us, cosmology is quite trivial, this question why it is important. On cosmological scales, gravity is really the source that dominates everything, the force that dominates everything. And so before I go into the gravitational actors, I will start with what we care about in cosmology, or how we do cosmology. Cosmology, as you know, describes the entire universe from its origin through the entire evolution. And it does it in a quite simple way, actually. So let me see. Cosmology describes the universe with only 2 fundamental pillars. The first one is the assumption that general relativity is the theory of gravity and the cosmological principle, namely that the universe is on cosmological scales more or less homogeneous and isotropic. So let me start with general relativity. I will introduce general relativity, but I would like to do that in 2 complementary representations. First, I will start with the geometrical representation, and then I will move on to the particle representation. So in the geometrical representation, in order to describe general relativity, I will make use on the 3 fundamental geometrical objects, namely curvature, torsion, and non-metricity. So this will allow me to introduce the geometrical trinity of general relativity. If you wish, you can see more. Let me see if I can. Here in this paper here, you can see more about this. So in this geometrical trinity, I will introduce general relativity a la Einstein, which is based on curvature that we are all familiar with. But then I will introduce a second formulation, which is completely equivalent but independent, based on torsion. And then I will introduce general relativity based on non-metricity. This is a third completely equivalent, but yet completely independent formulation of general relativity. So what do these geometrical objects represent? You are probably already very familiar with what curvature represents. So if you have a vector and you move this vector along a closed path and you come back to where you started, and now if this vector points towards a different direction than you started with, it means that your manifold has a non-vanishing curvature. How about torsion? So if your spacetime has a non-vanishing torsion and you have 2 vectors and you parallel transport them along each other, and now if this parallelogram doesn't close, it means that you have a non-vanishing torsion. All right, and what does non-metricity represent? Now if you have a vector and you transport it along a given path, the length of the vector field changes if your space-time has a non-vanishing non-metricity. Let me start then with general relativity a la Einstein that we are all familiar with, but just to be able to make the comparison. So we are then in a pseudo-Riemannian manifold, and our fundamental object is of course the metric, and the connection is then purely given in terms of the Christoffel symbols that themselves are completely determined in terms of the metric. So there isn't any new additional degrees of freedom associated to the connection. So you live in a space-time which is curved, but torsion vanishes and non-metricity vanishes. So you have to work with the Riemann tensor, which is given here. You see it has some derivatives acting on the Christoffel symbols and then some Christoffel symbols squared. It is a tensor with 4 indices. You can just contract indices, and then obtain a scalar quantity. And this uniquely then gives the Einstein-Hilbert action. And because of these derivatives acting on the Christoffel symbols, you have second derivatives acting on the metric. And so if now your manifold has a boundary and you perform the variational principle, then your variational principle is not well posed due to the second derivatives of the metric. And you need to add the given talk in your boundary term by hand in order to make your variational principle well posed. So let me then, okay, so just to the counting, we have the metric as our fundamental objects, which is symmetric, so it has 10 components, but the Einstein-Hilbert action has diffeomorphisms, which give rise to 4 first-class constraints, so they remove twice times this gauge modes, and at the end you have 2 propagating degrees of freedom. Let me then move on to teleparallel equivalent of GR. Now you live in a manifold based on torsion. And the connection is now the fundamental actor, let's say. And the connection has now this important piece, which is the contortion tensor, given here in terms of torsion tensor in this form. So now you live in a space-time which is completely flat, and non-metricity is 0, but torsion is the only non-zero geometrical object. Here is the definition of the torsion tensor in case you are not familiar. It's the antisymmetric part of the connection. Because it's antisymmetric, so it's antisymmetric in the mu-nu indices here. All right, so the fact that we live on a completely flat space-time has huge consequences in this formulation. So the connection then is forced to take this form here in terms of this lambda matrices. And so lambda is an element of the general linear group. So if you want, you have a translational invariance coming from this general linear group. And now you impose also that non-metricity vanishes. And this gives then a direct relation between your metric G and then this fundamental object lambda that comes in the connection. Of course, then the torsion is simply given by the antisymmetric version of that here. And I told you the torsion is antisymmetric in the mu-nu indices. It's a tensor with three coefficients. As you can see, you cannot build anything linear in torsion. So you need to go to quadratic order in torsion in order to build, to be able to write a scalar quantity, a Lagrangian. And so these are the 3 independent constructions that you can have at quadratic order in the torsion tensor, with this coefficient C1, C2, C3 being arbitrary coefficients. All right, and with Lagrange multipliers, you make sure that curvature vanishes and non-metricity vanishes. Only if you choose these 3 coefficients in this very specific way, you obtain an equivalent theory, completely equivalent to general relativity. So how does the counting now works? As I said, your fundamental object is the connection, or this 16 components in this 4x4 matrices here in this lambdas. You have the translational gauge symmetry, which again gives rise to first-class constraints. So this removes -2 × 4. And now if you choose these coefficients in this very specific way that you obtain GR, you obtain actually local Lorentz symmetry. Again, -6 here. At the end of the day, you have then 2 propagating degrees of freedom, as it should be if it's really equivalent to general relativity. Now, if you want to see the equivalence explicitly, if you take the standard Ricci scalar of the Christoffel symbols here on the left-hand side, you see it's directly related to this quadratic torsion Lagrangian with the coefficients chosen such that it's GR, up to some boundary terms, up to some total derivatives here. So these two formulations are completely equivalent up to total derivatives. So their equations of motion are completely equivalent. But at the level of the Lagrangian, they differ by boundary terms. Let me then move on to coincident general relativity. Now you have a manifold based on non-metricity. This is now your fundamental object. The actors are both the metric and the connection. And the connection has now this important piece, this deformation tensor given in terms of the non-metricity tensor in this way. Now you live in a space-time which is again completely flat, and torsion is zero and only non-metricity is non-zero. Here is the definition of the non-metricity tensor if you are not familiar. So it's the covariant derivative with respect to the general gamma connection acting on the metric. So this is the non-metricity tensor. So again, if you impose the conditions that we had, so that curvature vanishes, so you are in a flat space-time, imposes the same condition on the connection in terms of this lambda. And now imposing that torsion also vanishes has huge implications in this formulation. Namely, you see that the lambdas now representing the connection become pure diffs, this size here. And so the connection is given then pure in terms of this diffs in this form. And as you can imagine, by means of appropriate gauge choice, you can make that this connection vanishes completely, globally, everywhere. So this is quite intriguing property of this coincident general relativity that you don't have in these other two formulations. So again, it's a tensor with three indices. You cannot build a scalar quantity out of that at linear order. Now it's symmetric in the mu indices because the metric is symmetric. And so you need to go again to quadratic order, and because it is symmetric in the mu indices, you have now 5 independent contractions at the quadratic order. So I symbolically wrote them here, these 5 independent contractions with 5 arbitrary coefficients. And with Lagrange multipliers, we make again sure that curvature vanishes and torsion vanishes. And again, only if you choose these coefficients in this very specific way, you obtain an equivalent theory to general relativity. So these coefficients, when you choose them, they are then given in terms of here, these contractions. So if you again want to see the equivalence explicitly in terms of the comparison with the standard Einstein-Hilbert Lagrangian, so the Ricci scalar of the Christoffel symbols, you see you obtain exactly the quadratic non-metricity scalar here with the coefficients chosen such that it corresponds to GR. Again, the difference is some total derivatives, some boundary terms. So one nice point here that I already mentioned, that the connection vanishes. So in this coincident gauge, in this particular gauge where you make that the connection vanishes, then this quadratic non-metricity scalar becomes the Christoffel squared part of the standard Einstein-Hilbert Ricci scalar. Okay, so the Ricci scalar that has the partial derivative acting on the Christoffel symbol doesn't appear here. Okay. So let me mention a few nice properties of this coincident general relativity formulation. So there is no need for the Gibbons-Hawking-York boundary term for a well-defined variational principle. Remember, this was exactly due to the second derivatives acting on the metric. And in coincident general relativity, you have nowhere second derivatives, so you don't run into this variational principle problem. And one could also argue that it gives more direct contact with the particle description of general relativity, which I will show later. And so this is also nice that it gives a closer connection to the particle description. And so this improved action principle can also make huge differences in considerations of energetics, thermodynamics, and quantum theory that we are investigating in our group. So for instance, for the computation of the entropy of a black hole, or for the canonical quantization of general relativity, and so on. And yeah, and in coincident gauge, for some concrete purposes, it might be also easier to work in coincident general relativity because then you have just partial derivatives. And yeah, that might be easier for some calculation purposes. All right, are there any questions on this part?
Yes, I have.
Yes.
Can you hear? Yeah.
Yes.
So I'm a bit puzzled by your constraint on the Riemann covers to vanish. I mean, although you are saying it's equivalent to GR, standard Einstein-Hilbert action, but GR allows Riemann tensor can be non-trivial.
Yes.
Yeah. For example, I mean Schubert-Schultz geometry has non-trivial Riemann curvature. So your theory cannot have Schubert-Schultz the geometry, or could you elaborate?
So this is the whole difference, right? In one case, your interpretation of gravity relies strongly on the fact that space-time is curved. On the other hand, in this other formulation, you say your interpretation doesn't know anything about the fact that space-time is curved. So you are actually assuming that space-time is completely flat. And in fact, in the original formulation of general relativity, the fact that space-time is curved makes everything very, very complicated and difficult. And now here is Riemann is really exactly zero. But now in your Lagrangian, you don't have some Riemanns constructed. What you have is the non-metricity scalar. So you have actually the non-metricity tensor being your fundamental object, which is, again, as I told you, not about the space-time being curved, but for instance, that the lengths now are changing. So your interpretation of gravity has radically changed, fundamentally changed. And I'm saying that if you now want to compare it to your original formulation, you see that you obtain exactly these duality relations between these two descriptions up to this total derivatives.
As well as Lagrangian multiplier terms, right? The constraint terms. You didn't write down here, but there are also two constraints, these lambda terms.
Yes, there are these two constraints, but in this equivalence, they don't appear.
So, I mean, going back to my original question, can your theory describe Schubert-Schultz geometry?
Yes, it describes, sorry?
Yeah, Schubert-Schultz geometry, which is a non-trivial Riemann curvature.
Yes, I mean, everything physically that you were able to describe geometrically in the other formulation, you can do it now here. It's just that the physical interpretation is different. And in fact, here, if you look at this duality relation, there is an additional Riemann scalar here appearing, but Riemann of this not curly R with respect to the Christoffel, but this Riemann contracted appears here because it's zero, it doesn't come here in this duality relation. So yes, it's very fundamental that you have this in this Lagrangian, your non-metricity scalar, but then you have these two constraints that torsion vanishes and the Riemann vanishes. And your physical geometrical, like the geodesic equations, I mean, everything that you do physically in this geometry, you can do it as well. It's just not in terms of curved space-time, but in terms of this non-metricity interpretation.
Okay.
Question. Hello, question.
Yes.
For the two alternative formulation of GR, So it seems that the more general coefficient of CI, the Lorentz symmetry looks to be broken. Why is broken?
Yes. So actually, you can see that already for general relativity. Imagine you wrote the most general Lagrangian in terms of derivatives acting on the Christoffel symbols and then Christoffel symbols squared with arbitrary coefficients. And now you can see at this arbitrary coefficients, you see that, you know, if you want to get, for instance, diffeomorphisms and Lorentz symmetry, you have to choose these coefficients in a very specific way. And at the end, you obtain exactly the Ricci scalar of the Einstein-Hilbert action. And the same thing happens here. So from a more general theory with arbitrary coefficients, you see that symmetries pops up. This is very common in physics. It always happens that you know, symmetries require some corner of your space of parameters. So as soon as you move away from this C parameters chosen to correspond to general relativity, you obtain you lose some of the symmetries. Yes.
Okay, I see. So it basically came from the non-tensor nature of Christopher symbol.
No, the Christoffel symbols I gave you as an example, that what would happen in standard general relativity. And in fact, the fact that you have these specific coefficients that introduce symmetries, that also corresponds to whether or not you have additional propagating degrees of freedom on top of the two standard propagating degrees of freedom that arise when you have these coefficients in a very specific way.
Okay, I see. Thank you.
All right. So this was the gravity sector. So how about the coupling of matter fields? This is also a very important fundamental question, right? So you can also read more about that in this article here, but let me give you a quick answer to this question. So you might be aware of the fact that the very fundamental construction of general relativity itself, the standard a la Einstein, relies strongly on the minimal coupling principle, which basically states that all the matter fields couple only to the metric or its inverse metric and to the volume element, to the square root of minus g, but never to the derivatives acting on the metric. So this is the minimal coupling principle. So what happens when you try to apply this minimal coupling principle to the other formulation? So if you take this formulation, for instance, based on torsion, and you apply the minimal coupling principle, what you immediately see is that it doesn't work. So it gives rise actually to non-minimal coupling to torsion. Things like photons or gauge fields, they really want to couple to the torsion if you take the minimal coupling principle as some fundamental principle that you care about. Now, if you try to take the constant general relativity based on non-metricity and you apply the minimal coupling principle, then it works. You preserve the minimal coupling. So, you know, your gauge fields behave exactly in the same way as in standard general relativity. So that's good. And now considering fermions, the situation for the torsion formulation becomes even worse because fermions really wants to couple to torsion, and you have to make some ad hoc by hand manipulation in order to make them not to couple to torsion. But in the case of coincident general relativity, for instance, if you take the Dirac-Lagrangian, you see that the non-metricity doesn't couple to the fermions, so the connection doesn't couple to the fermions, and only the standard metric part. And so then fermions also behave exactly in the same way as in standard general relativity. So concerning coupling, one could summarize that the equivalence is maintained between coincident general relativity and standard general relativity. But as soon as you have torsion, you have to be very careful. All right. So now I would like to discuss about some geometrical extensions of general relativity. And one arises very immediately, one possible extension. And this is when you start from this equivalent formulation and you promote them to general functions. People have considered them, right? So you take, for instance, your standard Ricci scalar of the Einstein-Hilbert action and you promote it to a general function of the Ricci scalar. In the same way, you can do this also now for the non-metricity, this quadratic non-metricity scalar, and promote it to a general function. And similarly also for the torsion scalar. So even though the original formulations of general relativity, they were completely equivalent, once you promote them to general functions, they represent completely different theories with different propagating degrees of freedom. So could you have other consistent quadratic actions? This could also be a question. You could say, oh, I take now quadratic non-metricity and quadratic torsion and even some mixed terms with some arbitrary coefficients. And then can I choose these coefficients A, B, C's in a specific way that I modify general relativity so that I go beyond general relativity. So you can do that and you have then additional degrees of freedom, but there is usually strong coupling problems in this geometrical extensions, that some of the degrees of freedom, they lose their kinetic term on top of relevant backgrounds like Minkowski or de Sitter or FRW type of backgrounds. So in principle you can do, but phenomenologically you seem to run into strong coupling problems. Other extensions without additional degrees of freedom, do they exist? Yes. You could, for instance, consider such a Lagrangian where you have the volume element square root of minus g multiplying a function that depends on the inverse metric, and then this metric Ricci tensor that depends on an independent connection gamma. So this gamma is not the Christoffel symbol, but an arbitrary independent connection. When you have such a Lagrangian, then you still have two propagating degrees of freedom as in standard general relativity. You see effects only for high curvature. So when this piece is large, and since the connection now, the way how it enters here comes through an algebraic equation, so it doesn't have really differential equations, so it doesn't propagate. It's just an auxiliary fields that you can integrate out, and as a consequence, the matter field coupling changes. One specific example of such a general function is, for instance, the Bornfeld inspired gravity that one obtains very naturally from some string theory compactifications and so on. All right, so this is the geometrical part basically. Are there any further questions before I move on? Doesn't seem to be the case. All right, so then I will now play a Gedanken experiment, if you allow me. And I will imagine a universe in which Einstein did not exist. I know that would be very, very sad. I can imagine that you are making now like angry faces, but bear with me. So let's imagine a universe in which Einstein did not exist, but instead imagine a modern version of Einstein that existed. And this modern version of Einstein, which is what is important for this person, is that this person now sees gravity from particle physics perspective. To be fair, this modern version could be also a lady, a woman. it doesn't matter. So this modern Einstein, he or she would have learned all the standard techniques of particle physics description. He or she would not care at all about geometry. So we would have then eventually constructed GR, but from particle physics perspectives, and just years later. So thanks to Einstein, we had already quite early on, but we could have done it already also due to the techniques that we had in particle physics description. So in the same way as we describe the photon particle as the exchange particle between, for instance, two electrons, in order to describe the electromagnetic interactions, we could see gravity as the exchange of a graviton particle between these two objects, and in this way gives rise to gravitational interactions. So this is a whole change of, yet again, interpretation of gravity. Now we give up on the fact that space-time is curved or whatever. Instead, there is a particle. And in this particle representation, the GR representation, basically, that what corresponds to GR is given by a massless spin 2 particle. And this is really unique. We have seen in the geometrical representation the same theory we could describe in three different ways. But in the particle representation, there is really just one unique particle, and this is the massless spin 2. So why massless spin 2? We can appreciate that by reminding ourselves about the facts that we know about gravity. It's long range. Gravity is long range, so the particle associated to it should be massless. And it exists as a classical theory, so no fermionic particle. It can only be bosons of spin 0, 1, 2. And it is attractive, so it cannot be photon-like. So this excludes spin 1 particle. And it interacts with light. So it cannot be Higgs boson-like, so this excludes spin 0. And this uniquely then gives rise to spin 2, massless spin 2 particle as a natural candidate. So then how do you describe the massless spin 2 particle that I describe here by this h mu object? So then you write down your quadratic Lagrangian, the most general quadratic contractions in terms of derivatives on h mu, so quadratic in partial h, with these 4 coefficients being arbitrary, and now demanding that this massless spin 2 particle should only propagate 2 physical degrees of freedom, fix these coefficients in this very specific way. This is nothing else but the Fierz-Pauli Lagrangian, the linear Fierz-Pauli Lagrangian, and so in this way you have your propagator. Now you can also build interactions, and for this you take your quadratic Lagrangian and you apply this bootstrapping approach. So now you take your quadratic Lagrangian, and from this quadratic Lagrangian you compute the self-energy, the T mu nu associated to this Lagrangian, and then you couple it to itself via h mu nu, T mu nu. In this way you then obtain cubic vertices, and so on. And so now you take then this as your new Lagrangian, and you apply the bootstrapping to next order. So you obtain from that now the T mu nu alpha beta, and you couple it again to itself. And in this way, you obtain an infinite series of interactions of this massless spin 2 particle. And what is quite remarkable is when you sum this infinite series of interactions, what you obtain as Lagrangian is the coincident general relativity in the coincident gauge, where the connection is 0, which is basically the Christoffel squared part of the Einstein-Hilbert action. Okay, so this is the reason why I was telling you that in the geometrical representation, the coincident general relativity formulation has more direct contact to the particle representation, because once you sum this infinite series of interaction of this massless spin 2 particle, you obtain exactly the corresponding Lagrangian of coincident general relativity. All right, so then whatever your interpretation is of gravity, I would like to model the universe, right? So I have to build a model of the universe. I essentially have to solve Einstein's field equations, G mu nu equals to T mu nu, where now this T mu nu represent all the matter fields. But the equations of general relativity are very difficult to solve. So you need to have some fundamental assumptions, and there our second pillar comes into game, so the cosmological principle, namely that the universe is homogeneous and isotropic. With the help of this cosmological principle, I can then find exact solutions to Einstein's field equations. And these are exactly these FLRW models, in which my background metric depends on the scale factor, which has only time dependence. So when I plug this in to the Einstein's equations, I obtain this Friedmann equations where big H represents A dot over A. And I have also, of course, the equations of motions of the matter fields given here. So I can then basically parameterize the Hubble function here in this way in terms of the ingredients that I have in terms of omega matter, omega radiation, omega lambda. And then I can now take this Hubble function and compare it to observations. And when I do that, I obtain this simple model, the lambda CDM model, which says that almost 70% comes in form of dark energy. Then this 27% in form of dark matter, and then only roughly 5% makes out of the entire, like the matter field that we know. So this model is very, very simple, and it describes beautifully all of the cosmological observations, and it does a great job. Apart from this recently called H0 tension, that when you compare late time observations with the early universe observations, there seems to be a tension on what this Hubble parameter here, this H0, corresponds to. But other than that, it really works quite nicely, and it's a very simple model. So then another very important information we obtain from CMB, of course, as I told you. So when you take, for instance, these two patches very far from each other on the sky, then it raises immediately a question. You know, how can these two patches on the sky, which have never been in causal contact, have the same fluctuations, exactly the same fluctuation up to 10 to minus 5? So we cannot explain that unless we are willing to introduce an inflaton field that gives rise to an early phase of accelerated expansion. And in this way, we can then explain why these two patches have the same exact temperature, because they have been actually in causal contact. So this is the picture that we have. So we have GR, dark matter, dark energy, and the inflaton field. And with this, we can then describe the origin and evolution of the entire universe. But of course, there are very fundamental questions associated to these ingredients. So what is the quantum nature of GR? And also associated to that, we have the cosmological constant problem. Then what is the origin of dark matter? We never observed this, so this is still a fundamental question. We have no idea. And what causes these two accelerated expansion phases of the universe? So the dark energy and the inflaton. And is dark energy just a cosmological constant, or really a field that evolves in time, like the inflaton field? So in order to answer some of these fundamental questions, some people consider that what could do is, at least for cosmological phenomenology, is to assume that you have GR plus some sort of effective field theories that you might believe in it more or less, depending on maybe if you can motivate that from maybe string theory or so on. So some effective field theories, or you try to modify gravity and you give up on the assumption of GR, but also there, as soon as you modify gravity and you move away from GR, you introduce new additional degrees of freedom. So you see, in both cases, it doesn't matter from which perspective or which motivation you come, you're going to always introduce some additional degrees of freedom. These are some additional scalars, vectors, or additional tensors. And so you always introduce these additional particles into the game. So in the hope that some of these particles are going to describe some of these ingredients, maybe all of them if you are lucky. So then let me start with the scalar field, the Galileans. So these are special effective field theories, especially in the sense that they give rise to second order equations of motion. They have Lorentz invariance and locality, and they have also this shift and Galilean symmetry. The Lagrangians are invariant under these transformations here. In this way, you can construct all the allowed interactions, the derivative interactions of the scalar field. That was done here first in this paper here. And so you see second derivatives acting on the scalar field. You have these traces of this quadratic object here. And then you see that in L4, L5, you have these relative tunings of the parameters such that you have really second order equations of motion, and that only the scalar field propagates, that you don't have any ghost degrees of freedom. You can then build scalar tensor interactions by promoting this to curved space-time, and in this way you obtain then Horndansky interactions, which Horndansky himself introduced quite some time ago. And here you see this is basically the derivatives basically converted into covariant derivatives, and but in L4, L5, you have to be careful. When you do that, you actually have higher order equations of motion. And so you have to add some non-minimal couplings to the gravity sector in order to maintain that you have second order equations of motion. And that you have now only 3 propagating degrees of freedom, 1 coming from the scalar and the 2 coming from the tensor part. So these non-minimal couplings modify the gravity sector. But you can have homogeneous and isotropic solutions very easily by assuming that the scalar field has only time dependence. You can also do the same thing with a vector field. So you can construct effective field theories for a vector field. You do the same thing. So you assume you require that you have second order equations of motion, Lorentz invariance and locality, and that you have 3 propagating degrees of freedom associated to a massive vector field. So in this way, you can also construct all the allowed interactions here. And here you see, the Lagrangian goes up to the 6th order compared to the Galilean case. But you also see that similarly, you have to tune between these different coefficients in order to make sure that you have second order equations of motion and that you have only 3 propagating degrees of freedom for this massive vector field, and that there aren't any additional ghost degrees of freedom. You can also promote them to curved space-time, so then you have construct vector tensor theories.
Hello, Lavinia.
Yes.
Can I ask a question? So basically, if you assume an isometry direction, right, we're working in 4D, and if we have a killing direction, right, we could in principle reduce this down to 3D, and their vectors are dual to scalars. Could you imagine rewriting this as a scalar gravity theory?
Yes, I mean, when you take the
equivalent, right, with an isometry.
Yeah, if you take the vector tensor theories here, and now you project your vector such that you look only on its longitudinal mode, then you would obtain the scalar tensor theories, which are basically the Hondansky. So the longitudinal mode of the vector field, of the 4-dimensional vector field, is the scalar field. So the equivalence is not only as you did in 3 dimensions, but actually also in 4 dimension. You can build the equivalence if you only extract out the longitudinal mode. And so if you write a mu goes to partial mu phi, then you recover exactly the Hondansky theories from the vector tensor theories. Because then these additional terms here that are not present in the Galilean or Hondansky case, they actually vanish for the longitudinal mode of the vector field.
Thanks.
So here again, you have for L4, L5, L6, these non-minimal couplings. And so these non-minimal couplings then modify the gravity sector. As I said, you have these additional interactions here, which do not have the scalar equivalence. So even though when you take the longitudinal mode, these terms do not survive. So these are really pure intrinsic vector modes interactions. So concerning vector field and doing cosmology, it was long believed that a single vector field is in tension with the cosmological principle, that you cannot have a homogeneous anisotropic solution with one single vector field. And in fact, therefore, that is not appropriate. In fact, this generalized Proca introduced a radical change of view, because with this generalized Proca, you can actually have homogeneous anisotropic solutions with just one single vector field. And for that, the field configuration looks like this. So your vector field has a only non-vanishing temporal component that has time dependence. And just to give you an example, imagine you have a very simple Lagrangian with a kinetic term, with the general function of the vector norm, and some sort of a cubic vector Galilean type of interactions here. With this very simple, you can already have dark energy fixed points, so really cosmological solutions or homogeneous anisotropic solutions in which you also obtain dark energy phenomenology. And it also reduces the H0 tensions and delivers a better fit to data.
Hello, Lavinia, is F 0?
Sorry?
Well, what happens to F, the field strength? So A is basically, it's only got a temporal component and only depends on time. So is dA 0, or what's the definition of F?
Yeah, F is exactly the same the same definition: partial mu A nu minus partial mu A mu. And you're absolutely right. So
so it's pure gauge, right?
This temporal component is not pure gauge because it's a massive vector field. So you broke gauge symmetry.
For the mass.
But at the level of the background, this plays the role of an auxiliary field. So it's not dynamical, but it's nevertheless there, and it has algebraic equation. And so you can solve it, and it's gonna, if you want, you can integrate it out. And what it does is it changes the coupling to the matter field. So whatever is in your Friedmann equation on the right-hand side then changes. Excellent question, yes. So at the background level, this guy would not contribute to your equations of the A0, but at the perturbation level, it's going to contribute.
Thanks.
Other questions? All right. How am I doing with time? Am I supposed to stop here, or?
You've got more or less 10 minutes. Yeah.
10 minutes. All right, then let me try to go a bit further in these 10 minutes. So you have all these different cosmological models. I just gave you an example of one additional scalar field and one additional vector field. You can imagine that you know, depending on your motivation or on your preferences, you could consider many different types of cosmological models with different ingredients and degrees of freedom. And so now I think in order to discriminate or rule most of these models, we have to impose some consistency checks. And in my opinion, this comes hand in hand with both theoretical consistency checks as well as observational consistency checks. In the theoretical consistency checks, I think one can already make quite some damage, rule most of these models away, rule them out by considering the following as suggestions. So first of all, you check that the number of degrees of freedom are the right ones, that you don't have any ghost degrees of freedom. Otherwise, I mean, you can really throw away your Lagrangian. That you don't have any instabilities, for instance, for cosmology or black hole physics. When you look at perturbations, make sure that your perturbations do not suffer from ghost or gradient instabilities. Then there is this whole swampland business, which basically tries to put constraints coming from UV, from the assumption that your effective field theory should be embeddable into string theory or some sort of a quantum gravity theory. Then there are these positivity bounds. This is again a restriction coming from the UV. If you want to have Lorentz and local UV theory, then this has direct implications on the scattering amplitudes already at tree level of your effective field theory. And so you can use it to restrict it. And quantum corrections. So these are Lagrangians. As I showed you, these coefficients have to be tuned in very specific way in order to have symmetries, in order to have the right propagating degrees of freedom. And so then the question is, are these classical Lagrangians stable under quantum corrections? So let me give you quickly some of this, how they can be applied. For instance, this positivity bounds that I told you, that comes from the local Lorentz invariant UV completion down to your infrared theory. So these are then direct, this has direct implications on the scattering amplitudes. Just to give you an example, imagine you have the cubic Galilean and the quartic Galilean, and you want them to be able to be embeddable or to come from a local Lorentz UV complete theory. Then when you apply these positivity bounds, you obtain this constraint here on this cubic and quartic Galilean coefficients, and you have to be basically on this in this white regime here in order not to have any obstruction for a local Lorentz invariant UV completion. So you see, in this way you obtain additional theoretical constraints on your parameters. So there is also this interesting soft bootstrap program in which you can basically classify all the effective field theories and their symmetries, even if you don't know them up first when you start to construct them. So you can discover new symmetries. Just to give you an example, imagine you have Lagrangians like this, where you have a kinetic term applying some function of partial rho pi. This rho basically characterizes the number of derivatives per interaction. So if you want, it's the power counting number. Now, an important limit in this soft bootstrap program is when you take the amplitudes, the scattering amplitudes, and you send one of the external legs, their momenta, to 0, and you look how fast the scattering amplitudes goes to 0. And this is given by the P to the sigma. So sigma characterizes the soft degree, so characterizes the power at which amplitudes vanish in the soft limit. So here is an example taken from this paper where you can characterize all the different scalar theories depending on their soft behavior. So rho here versus sigma. You see Galilean sits here with rho equals 2 and sigma equals 2. And actually, there was a special Galilean recognized or recovered by applying this bootstrap program with a better soft behavior with sigma equals 3. And so let me mention that one. So if you have the Galilean theories, you have this invariance under the Galilean symmetries. And now imagine you erase away the cubic and the quintic Galilean interactions, then you obtain the special Galilean. And the special Galilean has an enhanced soft behavior P cubed, and the symmetry is also enhanced. So it has this non-linear part of the symmetry. And so this was really discovered with this enhanced symmetry by applying this soft bootstrap program. So as you can see, it's really a powerful tool to characterize all your effective field theories and their symmetries. Then concerning quantum corrections, let me also give there an example. We know that Galilean interactions are stable under quantum corrections. There is this non-renormalization theorem. And we were recently also able to compute all the one loop divergences in this closed form in terms of the some effective metric that depends on the scalar field and its derivative. So yeah, from this effective action, one loop effective action, you can then obtain all the endpoint functions. So imagine now you take this Galilean, let's say cubic Galilean interactions, and then you introduced a term which breaks the shift and Galilean symmetry, for instance, like this one. Now, because it depends on the pi itself, it breaks this Galilean and shift symmetry. But nevertheless, so you would assume that, oh, your nice quantum correction behavior would be lost because you lost the symmetry. But nevertheless, we were very surprised, and we were able also to establish a non-renormalization theorem also for this effective field theory, even though the shift and Galilean symmetry was explicitly broken. All right, but in this way, you can put constraints on your effective field theories. Similarly, for the vector field, we were able to show that all these Lagrangians, all these relative tunings, they are basically stable in the sense that all the counter terms that you introduce, they are suppressed with respect to this classical Lagrangians, the interactions that are relevant for you or for the cosmological or black hole applications that you are interested in. All right, another business which is very active is this swampland program. So there one tries to divide effective field theories into the landscape and the swampland. The landscape, of course, are those that can be successfully embedded, and the swampland are those that do not have any UV completion. And a given effective field theory has to satisfy some condition in order not to land on the swampland. These are like several conjectures there, like big gravity conjecture, distance conjecture, no global symmetry, de Sitter conjecture, and so on. The one which is probably most relevant for cosmology is the de Sitter conjecture, which basically states that the cosmological constant is very, very hard to get from string theory. But it's very easy to get a scalar field from string theory. From the compactification of the higher dimension, you end up having scalar fields with some potentials, and therefore the potentials have to satisfy this given condition. So this part here on the potential should be bigger than some order of one parameter in order for your effective field theory not to land on the swampland. And so this has, of course, huge implication for the dark energy. So imagine you have a quintessence model, then you can actually try to combine both the de Sitter conjecture and the different cosmological observations. But we are standing basically in front of two possibilities, and the future observations are going to show which one is basically more likely to be true. So if dark energy is the cosmological constant, And if the observation really do not see any indication away from the cosmological constant, then string theory has to work way more harder to get it more naturally. If you want, then you would be pushing string theory in an uncomfortable corner. Or if dark energy is a scalar field, then the Sitter conjecture can be used in order to have additional constraints in order to constrain even further your dark energy model. So with Ian, we have been also looking at in more detail to some quintessence model and show that whether or not actually they are doing a better job in explaining the observational signatures, also in terms of explaining the H0 tension. All right, I think my 10 minutes are over here and I better stop.
Yeah.
Thank you very much for your attention.
Thank you very much, Lavinia. Yeah. Okay, so we're now open for questions or comments. Any lingering questions?
Question?
Yes.
So regarding the Galilean theory, so what's the speed of graviton looks like? I think it's quite complicated. I mean, whether it's it is just the speed of light or more than that.
Mm-hmm. So it depends on what you're asking. If you are asking on the gravitational wave speed on cosmological
Right.
backgrounds,
Mm-hmm.
I might have a slide on that. Can you see that?
Yeah.
So yeah, if you have the scalar field, the Galilean or Hondensky, and now you want to just use this scalar field in order to describe dark energy.
Mm-hmm.
And so you have a cosmological background in which you are interested. And on top of this cosmological background in which pi plays the role of dark energy, and now if you look at the perturbations, then the gravitational waves have only luminal propagation if you get rid of this entire interactions here. Mm-hmm. So this has actually huge implications. I see that as something positive, you know. So I mean, I didn't have time to actually go through the observational consistency after you do the theoretical consistency checks. And actually this channel of gravitational waves is going to be you know, very, very strong and powerful tool to, you know, either rule out or put some of the theories into some uncomfortable corners. So in the case of the scalar field, these interactions, you would get rid of them. In the case of the vector field, you would also get rid of those interactions if you want to have luminal gravitational wave propagation. Does this answer your question?
Yeah, so that means otherwise you have generally speed of graviton which is different from the speed of light.
That's right.
Yeah, okay.
Yes. If you move away these operators, then they are equal.
Okay, thank you.
Other questions or comments?
Hello. Hi, thank you for your time. I have two questions, naive questions.
Yes.
So first of all, for your generalized Proca, if you put in a Bianchi spacetime, how generic is the isotropic fixed point? Or do you get attractors that are anisotropic?
Yes, yes.
So
yes.
So it doesn't generically isotropize like the simple vector fields do.
So if you have Bianchi type of solutions in which your vector field has spatial components, let me see, where was it? Then, you know, the spatial components there, then at the level of the equations of motion, they are going to give rise to new fixed points, right?
Yeah, so for simple vector fields, during inflation, the anisotropy will just, you know, will just decay. But I guess for these models, it's not guaranteed.
Yeah, so for this, what you could do is, for instance, when you take this homogeneous and isotropic solutions, and you look at perturbations on top of such solutions, and when you look at the vector perturbations, if they were not decaying away, then it would mean that, you know, as soon as you move away from that homogeneous and isotropic solutions, you would run into the, you know, not isotropic solutions.
Yeah.
But what you see is exactly that you have a fixed point in this sense that these vector perturbations actually they decay away in the same way as in standard general relativity.
So it's perturbatively stable, but there's other fixed points.
Yeah.
Okay, I had one of the stupid questions. So can you build ghost-free massive gravity from your non-metric interpretation of GR?
Yes, very good question. So in the case of the geometrical formulations of different theories, especially those ones here, as I told you, if you have some quadratic Lagrangians in this way, and you don't choose the coefficients such that you obtain GR, you can actually choose coefficients such that you have two spin 2 fields, so like in massive gravity or actually by gravity, and then additional 2 form, and you might have also additional scalar fields. But what is true is that you can that you end up having massive gravity or by gravity type of theories here if you choose the coefficients in a specific way.
Okay, that's cool.
So you can obtain massive gravity type of theories, but rewritten in a geometrical sense, basically.
Okay, thank you.
Any more questions or comments? In the room, we may be out of questions or comments.
Sorry?
In the room, we don't appear to have any more questions or comments. So I guess
All right.
Line have a question or comment? Anything pressing? If not, okay. If not, I guess, Lavinia, we can thank you very much for a very comprehensive overview of the exciting prospects that are there outside of GR. Actually, most of the introduction I hadn't seen before, right? So it's good to see that there is a zoo of things. Okay.
Thank you very much for having me here.
Yeah, thank you very much for your time. Okay.
All right. Have a good day.